Hello everyone, welcome all to Physics with Astronautics.
I was born to fight. Baby, I was born to fight. Baby, I was born to fight.
In this video, we will discuss about the HC Verma question. So let's begin. And so here is our first chapter, that is Introduction to Physics, and we will start with the questions with short answer. So our first question is: the meter is defined as the distance traveled by light in 1 by 299,792,458 second. Why didn't people choose some number such as 1 by 3 into 10 to the power 8 second, and why not 1 second? So here our answer will be: CGPM decided in its 2018 meeting that all the SI based quantities will be defined in terms of certain universal constant, and this constant will be assigned fixed numerical value by definition. So 1 meter is the length that makes the speed of light in vacuum to be 299,792,458 when expressed in unit meter per second, where the second is defined in terms of cesium frequency delta nu cs. And again we know that 1 second is the time that makes the unperturbed ground state hyperfine transition frequency delta nu cs to be 9192631770 when expresses in the unit hertz, which is equal to second inverse. So because this is the constant, so we can't change it. Then, and here is our second question, that is: what are the dimension of volume of a cube of as A and volume of sphere of radius A? And the third question is: the ratio of volume of a cube of as A to the volume of sphere of radius A. And here is our solution. We know that the volume of cube of as A will be defined as B is equal to A cube. So here the dimension will be, that is length cube, and we can write it as L to the power 3. Then the volume of sphere of radius A. So the volume of sphere of radius A, we know it is as 4 by 3 by A cube. Again we know that the numerical value have no dimension. So here the dimension of volume of sphere of radius A will be equal to L to the power 3. Then the third question asks: the ratio of volume of cube of as A to the volume of sphere of radius A. So here the ratio will be equal to A cube by 4 by 3 by A cube, and which will be equal to 3 by 4 pi. Because we know that the numerical value have no dimension, so here the quantity will be dimensionless. And here is our third question, that is: suppose you were told that the linear size of everything in the universe has been doubled overnight. Can you test this statement by measuring sizes with a meter stick? Can you test it by using the fact that the speed of light is universal constant and has not changed? And what will happen if all clocks in the universe also start running at half the speed? So here our solution is: first it has been asking that can you test this statement by measuring sizes with a meter stick. So no, we can't test this statement by measuring sizes with a meter stick if the linear size of everything in the universe has been doubled overnight, because the meter stick will also become double by its linear size, because this is also matter, so that we can't experience any kind of changes by using meter scale. So let's take a example. So let it is a matter and this is our scale. So by measuring it we can find it as 20 centimeter. So again, in the overnight, when the matter will become double in size, also the scale will become double in size. So again here we can see that there is no difference in the measurement. And the second question was asking that can we measure it by the fact that the speed of light is universal constant? So the answer will be yes, because if the light taking 1 second by crossing a matter, then after the event, that is the double in linear size, it will take 2 seconds, and we can feel the changes here. Then third question says if all the clocks in the universe also start running at half the speed, that is the clock slows down, which means the travel of light takes 2 seconds instead of 1 second. Means every event takes double time to complete by its actual time. Then, if all the terms in an equation have same units, is it necessary that they have same dimension? If all the terms in an equation have same dimension, is it necessary that they have same units? And here the solution we can see that is for the first question the answer will be yes. If all the terms in an equation have same units, it is necessary that they have same dimension. But for the second question, the answer will be no, because if all the terms in an equation have same dimension, it is not necessary that they have same units. For example, we can see the angular frequency and the frequency. Both have the same dimension, that is here omega, that is the angular frequency, is equal to 2 pi by t with dimension t to the power minus 1, and here the unit is radian per second. But when we'll see the frequency, the formula is 1 by t, and here the dimension will be t to the power minus 1, which is equal to the angular frequency but differ in unit, and that is second inverse. Then if two quantities have same dimension, do they represent same physical content? And here the solution will be, we can see it, or we can solve it by two example. That is the dimension of work is F dot S, that is force into distance, and this will be m1 l1 t minus 2, that is the dimension of force, and here the dimension of length will be l1, and the dimension of work will be m1 l2 t minus 2. Again we can see the dimension of energy, that is by 1 by mv square, and here this will be m1 l2 t minus 2. Here we can see that two different physical content with same dimensional formula. So it is not necessary if two quantities have same dimensions, they represent same physical content. Then it is desirable that the standards of units be easily available, invariable, indestructible, and easily reproducible. If we use foot of a person as a standard unit of length, which of the above features are represented and which are not? So here the solution is, here you can see the foot. So if we use foot of a person as a standard unit of length, so yes, the foot is easily available but variable by different persons. If we take the foot of a child or an adult, obviously it will differ by size. Then this is dexterable, and the lastly easily reproducible, that is we can measure it by one, first take one step, then the second, then the third, then the fourth. So the feature absent are invariable and indestructible. And here is our question 7, that is the last question of this session, and here it has been asking that suggest a way to measure the thickness of a sheet of paper and the distance between the sun and the moon. So first we have to measure the thickness of sheet of paper. So we can measure the thickness of sheet of paper by taking a number of paper, let it be n, and then measure the total height of the sheet and then divided it by the number of sheets. So let this is n number of paper and here is our scale. So let the height measured is xm. So let it be with height xm. So the thickness of a single sheet of paper will be x by n, that is the height divided by the number of paper. Again, we can calculate it by the using of a screw gauge. And the second question is the distance between the sun and moon. So we can measure the distance between the sun and the moon by the Pythagoras theorem by taking the sun earth distance and earth moon distance, which is known to us. Again, we can calculate it by the luminous intensity. So I hope you all enjoyed this session. So for more videos, please do like, share and subscribe. Thank you.